Yeah.
Coming up, it's my great pleasure to introduce my dear academic big brother Chao from Chicago Statistics to talk about Minimax estimation for phase synchronization.
Thank you so much,
the
Dana.
floor is all yours.
Can you hear me?
Yes.
Oh, great. Okay, it is my great pleasure to tell you about some of the recent progress that we have for this problem of phase synchronization. Actually, the title I submitted for the workshop was Iterative Algorithm for Discrete Structure Recovery, which is a general framework that's supposed to include phase synchronization as a special case. But last night, when I was preparing the slides, I realized I don't have time to go through all the details in the general framework. So maybe it's a good idea to just focus on this problem instead. And this is a joint work with my wonderful collaborator, Anderson Zhang, who is currently faculty at Wharton. He is actually going to give another talk on Thursday in this workshop. So let's start with the studying of phase synchronization. So we observe YJK, it is understood as a noisy version of the pairwise difference of two angles. And the goal is to estimate these angles Z1 through Zn. So each Zj, it is a complex number. The only constraint is the complex number Zj has norm 1. So for a complex number has a unit norm, you can always parameterize that by an angle. That's why Zj times the complex conjugate of Zk is understood as the difference of two angles. And the noise variable is just standard Gaussian. Here, the standard Gaussian is in a complex space. It is defined as both the imaginary part and the real part sampled IID from normal 0, 1 over 2. And our goal is to estimate these angles Z1 through Zn under the normalized L2 loss. So here you notice the loss definition. We put a minimization over a global rotation. The reason is because if you rotate all the angles by the same amount, then the joint distribution of these data will not be changed. So this minimization is to take care of this identifiability issue. So the problem is quite famous in the community of applied mathematics and has been studied by many people. And there are three main algorithms that have been discussed and studied in the literature. The first one is the maximum likelihood estimator to maximize the log likelihood function. And if you do some simple manipulation, it is equivalent to this quadratic programming algorithm, problem. But since here we have the constraint, which is also quadratic, so this is a QCQP, it is known to be computationally hard. It looks simple, but you cannot actually compute it in in polynomial time. That's why people also consider the following two approximations. And the first one is called generalized power method. The idea is at each iteration, you want to update the value of each angle, Zj, according to this formula. So if you look at the numerator, it is just one of the entry of the product between the data matrix Y and the vector Z, right? That's why it's called the power method. You first compute a product between Y and Z. And then for this vector, what you do next is to normalize each entry of the vector so that each entry has norm 1, because you want to estimate angle. That's why you should project the vector into. Okay, that's why the algorithm is called the generalized power method. And the second approximation to MLE is a convex relaxation by a semi-definite program. So to derive this SDP, it's actually very simple. You just need to rewrite the objective function of MLE as the trace inner product between two matrices, the data matrix Y and then the matrix ZZ transpose. So you want to regard this as an optimization over the matrix argument, ZZ transpose. And then what does the matrix ZZ transpose satisfy? Well, it satisfies two requirements. The first one is all the diagonal entries are 1. And the second one is ZZ transpose is PSD, right? And this gives you the two constraints that you have in SDP. It is convex, so it can be solved efficiently. And these three algorithms has been well studied in literature. For example, the 2017 paper by Afonso Bandera, Nicholas Fumo, and Messinger shows that the mathematical estimator satisfy the error bound with respect to this loss sigma squared over n. So this is just the classical parametric rate, because here we have the problem with sample size n squared, and the dimension is n, right? So this is just the classical dimension over sample size rate. And you can also show this is the minimax rate of the problem. So sigma squared over n is the minimax rate that can be achieved by the mathematical estimator. So what about the other two estimator? Well, in the same paper by these three authors, they actually proved this very nice result that shows the tightness of the SDP solution as long as an extra condition sigma squared s at most of order root n is imposed. Under this condition, then the solution of SDP is tight in the sense that it must be rank 1 and can be factorized into the outer product of the solution of the likelihood optimization. Okay. And for the generalized power method, Nicholas Fumo himself back in 2016 proved as long as you initialize the GPM algorithm from something consistent, such as the eigenvector of the data matrix, then you can show the algorithm converges to the mathematical estimator as long as the condition sigma squared is at most of order n cube is imposed, right? So by the connection of GPM and SDP to MLE, you can also claim these two algorithms also achieve the optimal minimax rate sigma squared over n because of the convergence. Okay, and the two results have been improved recently by this paper, Chao and Nicholas Fumo. They used the level out argument in 2018 and was able to improve the condition significantly to sigma square as at most of order n over log n. Okay, so if you remove log n, then this is the sharp condition. So this is actually, as I will discuss later, slightly stronger than what is necessary. Okay, and under the same condition by the same author, they also was able to establish the sharpness, the tightness of SDP, and showing SDP is rank 1 under this condition. Okay, so this is what we know as the state of the art for the phase synchronization problem in the literature. If you look at the results, there are some additional questions you can ask. For example, now we know sigma squared over n is the minimax rate. What about the leading constant? Can we figure out a sharp constant? And if so, can we show some of the algorithms that we have here are able to achieve not only the minimax rate, but also the constant? Maybe some of them cannot. Well, this is what we want to present in our results. But I would actually like to present the results in a slightly more general setting by allowing the possibility of missing data. So I'm going to introduce a random Adel-Shreni graph here. The adjacency matrix has elements A, J, K that follows I, the Bernoulli distribution with probability parameter P. So if Aij is 1, that means there is an edge connecting J and K. If this happens, then you can observe YJK. That's the pairwise difference of the J's angle and the K's angle. Otherwise, if AJK is 0, then you have a missing data. So we allow some missing data by imposing this, by only assuming we have a partial set of the pairwise relation between the angles. And it's the same problem that we want to estimate the angles Z1 through Zn under this loss function. So this is the main result. Under these two assumptions, and I will come back to the assumption later. First of all, we have a minimax lower bound. So if you look at the result, when P equals 1, indeed, sigma squared over n is the minimax rate. But for general P, the minimax rate should be sigma squared over np. And also, we characterize the leading constant. The optimum constant should be 1 over 2. Moreover, we show that all the three algorithms are exactly optimal, not just the rate, but also the leading constant as well. So the MLE GPM initialized by the eigenvector of the data matrix, and the SDP solution with an extra post-processing step by extracting the eigenvector will all achieve the minimax optimality. Okay, so now let's discuss these two assumptions. So the first assumption says that the sigma squared should be of smaller order than MP. So when P equals 1, then you may compare this one to the previous condition that is in literature. So the best condition that we have in the literature to establish the sharpness, the tightness of SDP and GPM is by Zhong and Bull. They require sigma squared to be of order n over log n. So here, when P is a constant, then it's of order little o n. It's better. But for general P, the condition becomes sigma squared is little o of np. So this is equivalent to saying that the minimax risk goes to 0, right? So in a sense, it is the necessary sufficient condition for consistency. Of course, for those of you who are more ambitious, you may be wondering what if sigma squared is of the same order as np. This is the regime where the signal to noise ratio is a constant. It's actually also a very interesting setting, even though in this setting, the minimax risk is actually a constant, but it is still interesting to characterize what exactly the constant is. What we know is when P equals 1, if you look at the results in the literature, then various numerical experiments will tell you that none of the 3 methods are optimal, okay? When in the regime where the signal to noise ratio is a constant. And when P equals 1, when the signal to noise ratio is a constant, then in the literature, we know that the approximate message passing algorithm, AMP, is able to achieve the optimal constant. Okay, but when for general P, when the signal to noise ratio is a constant, this is still an open problem. And the second condition that we need is P is at least of order log n over n. This is just to make sure that the random graph is connected. It only has one component. Okay. We also have additional result for SDP because the output of an SDP is a matrix. So if you are only interested in matrix estimation, if you want to estimate the matrix ZZ transpose under the normalized Frobenius norm, then we have a lower bound for that, and SDP without any post-processing step directly achieve this error as well. All right, so this is the result. And in the next part of the talk, I'm going to tell you how we can actually establish these results. But instead of giving you directly the mathematical proof, let me just slightly deviate from my topic and tell you this paper. This is a paper that appeared back in 2016, written by Yu and Harrison Zhou. It's a wonderful paper. It analyzed the statistical property and algorithmic performance of the K-means algorithm that people use every day in the context of Gaussian mixture model. Okay, so if you have a Gaussian mixture data generated from a Gaussian mixture model, then you just run K-means. In this paper by Lu and Zhou, they were able to show that in terms of the clustering error, the error will go down exponentially to the minimax clustering error for Gaussian mixture model, so which characterize both the statistical optimality and the computational efficiency of the algorithm. The reason I want to mention the paper here is I will try to convince you actually mathematically the Gaussian mixture model and the phase synchronization model, they are quite similar, and actually they have the same mathematical essence. And the K-means iteration and the iteration that you see from the generalized power method, they can be derived from the same mathematical principle. They're actually the same product. Okay, so this is by viewing both models as special cases of this general structure linear model framework. So this is a framework which I proposed back in 2015 together with Arthur van der Waals and Harrison Zhou. The goal back then was to understand the behavior of a particular posterior distribution for a general class of high-dimensional models, and our goal is to use this general framework to include many high-dimensional models that people care. But it turns out, for today's purpose, this framework is also proved to be useful to understand the performance of K-means and the generalized power method in phase synchronization. So in this framework, what you have is a data object, Y. It can be written as the sum of a signal part and a noise part. Right? Let's just ignore the noise part. The signal part has 3 components. The first component is the structure parameter Z that we are trying to estimate. So here, Z stands for the clustering label in the Gaussian mixture model. And in the context of phase synchronization, it is just a vector of n angles that you are trying to estimate. Okay. And then we have the second component. It is the linear operator. I use the notation script X to denote that. The linear operator is indexed by the structure parameter. So if you change the value of Z, the linear operator will be changed. And finally, we have the parameter. This is the model parameter B, which is the last ingredient of the structured linear model. So what the linear operator does is to map the parameter from the space to the space where the data lives. Okay. And furthermore, I'm going to impose the assumption that the parameter B lives in some parameter space, and the parameter space is potentially of low dimension. It is also parameterized by the same structure parameter that you see as an index of the linear operator as well, right? So here I want to emphasize that the structure parameter Z appears in two positions, right? The first as the index of the linear operator, and also as the index of the parameter space. Okay, so with this general framework, you can actually rewrite many familiar models as special cases. For example, in clustering, we have the Gaussian mixture model. Here, the corresponding linear operator just maps the matrix that consists of k clustering centers to the expectation of the data matrix. And for the ranking task, what we have here is a very simple pairwise difference model. And what the linear operator does is to map this one-dimensional parameter beta to the expectation of the data matrix. And then finally, the linear regression model is also a special case. This is kind of obvious because the linear operator is fully determined by the design matrix of the problem. Okay, so it turns out this is a very good framework, and it allows us to write down a unified algorithm to solve all kinds of different problems with a single approach. So here's a way that we can construct such a unified algorithm. The first step is to write down some local statistic Tj. Okay, so the goal is that we hope is Tj can contain some information about the jth component of the structure parameters we try to estimate. So the only mathematical requirement we have for Tj is its expectation should be a function of both the model parameter B and the jth component of the structure parameter Zj. Okay, so once this is true, then you can just write down the following naive estimating procedure. So this is just a search over all possible values A such that the L2 difference of the statistic Tj and the proposed expectation is minimized, right? So the least square procedure, there's nothing special about it. But actually, you cannot use this algorithm in practice because you do not know the model parameter B, right? Because that's the only problem that we are trying to address. But the good news is that we have assumed the model parameter B belongs to some parameter space that is of low dimension, and it is also indexed by the same structure parameter Z that we're trying to estimate. So in a sense, if we know Z, somehow we can use this knowledge to estimate B, but if we know B, we can use this least square formula to estimate Z, right? So this naturally gives you an procedure that you can write down. This is exactly what we are going to do by replacing B with some estimator B hat of Z, right? So this B hat of Z is a global least square procedure, but assuming B belongs to the parameter space indexed by the structure parameter Z, okay? And we also have a theorem to guarantee the statistical error convergence for this general iterative procedure. But first, let me introduce some notation. We are going to analyze the error of this iterative procedure using this loss function. This is just the sum of the L2 difference between the mean function, and here the only difference between the two mean functions is in terms of difference of the structure parameter. Here, the first place we have Zj, the second place we have Zj star. Okay. And we for those of you who are interested in Gaussian mixture model, if you want to do clustering, then for clustering, what is natural to measure the error is the Hamming loss, right? Then there is a trivial lower bound. You can lower bound the L2 loss by a Hamming loss multiplied by the signal difference. Okay, so as long as you can obtain a bound for the L2 loss, this naive inequality will also give you a bound for the clustering error. All right. So next, I have two empirical process type conditions that I impose using these abstract notations. So here, I apologize for being sloppy. If you want to know the exact definition of the difference function, these will be made specific in the paper. You can look at definition, but it's quite complicated. I don't want to go to details. But roughly speaking, what I require is that the ratio between the difference between the two mean functions and the corresponding difference in terms of loss is of smaller order, is of order a little O1 with high probability. And I also want this to be uniformly holds within a neighborhood of the truth with radius tau. Okay, it turns out this tau will characterize the domain of attraction of the iterative algorithm. And in the second condition, it is just require the difference between the two mean functions. If B star is replaced by an estimator, which assumes the knowledge of Z star is also of little O1 with high probability. So under these two conditions, we can show as long as you initialize the algorithm within the radius of tau, here the tau is the same tau that appears in the previous condition. And then the algorithm in terms of the outer loss will converge to what is called the ideal error at an exponential rate, right? So here, ideal error, again, I do not make specific here, but you can specialize that in many specific problems. It will usually give you the minimax rate of the problem, okay? All right, so let's work out the specific example. So the first example we are going to do is to specialize this idea to the Gaussian mixture model. Okay, so we have the Gaussian mixture model. The ith data point is a d-dimensional Gaussian vector. The expectation is given by theta sub zi. Here, zi is the clustering label of the ith data point. So what would be a natural local statistic? Well, just take the local statistic to be the ith data point, right? And then compute its expectation. So the expectation function is theta sub a. With this specification, you can work out the general iterative procedure. It turns out to be exactly the k-means iteration, right? And if we specialize the theorem to the context of Gaussian mixture model, what we can get is the convergence guarantee for the k-means algorithm under this setting. So under the assumption that the number of cluster k is a smaller order of the sample size and the signal to noise ratio condition holds, you can show that in terms of the clustering error in the Hamming distance, it goes down to the minimax rate of the problem with exponential convergence algorithmically. Okay, as long as you initialize the algorithm by something good such as spectral clustering. Okay, and now I want to emphasize this is actually not my result. This is precisely the result by Yudo and Harrison Zhou. The point here is to tell you you can actually rediscover this result from a more general perspective. Okay, so now we are ready to actually analyze the phase synchronization problem, use this more general perspective of analyzing the k-means, right? So here, this is our phase synchronization problem. I just put everything in matrix notation. So we have the data matrix Y written as ZZ transpose plus the noise complex Gaussian random matrix. So the first problem that you notice here is that the mean structure is ZZ transpose, right? It turns out to be a quadratic function in terms of Z. But our general framework is called the structural linear model. So what we need is linearity. Okay, so this is an issue that we have. But turns out this is actually where we can take advantage of the flexibility of this structural linear model. So previously I emphasized a nice feature of this framework is that the structure parameter Z can actually appear in both places. First, as an index of the linear operator, and second, as an index of the parameter space. And this turns out can resolve this quadratic dependence issue. And we are going to do that. So what we can do is to rewrite the model as Z beta transpose. Okay, just by rewriting Z as beta. Okay, and then this gives us the corresponding linear operator, which maps beta to Z beta transpose. Okay, this is a well-defined linear operator. And what about our parameter space? well, the parameter space for beta is just this trivial space indexed by z. It turns out to be the space that only contains one element, z, right? If you do that, then you can, this is how you can recognize space synchronization model as a special case of the structured linear model framework. Now we have a representation that is linear in z instead of quadratic, okay? And then we can derive the algorithm. And the local statistic is just the ith column, or you can also use the ith row of the data, yi. And the mean function is a times beta, okay? And we can, with these two choices, we can write down the general iterative procedure as is. Okay, so let's try to solve these two optimization problems. The first optimization problem is trivial because if you look at the constraint, give you a singleton. So trivially, the answer to the first optimization problem is just the z value from the last step. Okay, and then you can plug the relation beta t equals zt minus 1 to the second optimization problem. And if you solve that, what you can get is exactly the iteration formula of the generalized power method. Okay, so indeed, the generalized power iteration and K-means algorithm are the same. They can be derived from the same approach. Okay, and if you want to allow the possibility of missing data, you can simply replace yjk by the product of ajk times yjk. This is just to be more general. Okay, so now I'm trying to I will give you an analysis of this iterative algorithm, and this will give us a sharp upper bound for the phase synchronization problem. So I'm going to define a notation f. F is a map that summarizes the evolution of the algorithm given by a generalized power method. Okay, and for this f, we have the following lemma, which says under the same two assumptions that we have for the main theorem, for any gamma that is of order little o1, there exists some delta also of order little o1, such that uniformly over all z in the neighborhood of z star, the one-step iteration of z satisfy this inequality. Right? So here, if you regard z as the current step, then f of z is the next iteration result. Okay, so in terms of loss function, it is bounded by two terms. The first term characterizes the optimization error, which is the error from the last step with an extra factor given by delta. And then the second term is exactly secant squared over 2np. This characterizes the statistical error for the phase synchronization model. Okay, so with this result, an immediate corollary is that the generalized power method, after sufficient step of iteration, will achieve exactly the minimax optimality. Okay, so that's the first result that we can derive from this lemma. The second result is the theoretical guarantee for the mathematical estimator by recognizing that the solution of the MLE is actually the fixed point of this map F. Right? This means if you start the generalized power method at the solution of MLE, it will stay unchanged. Okay, and because of this property, the previous lemma that characterized the property of the F also give you the statistical optimality of the fixed point of F, which is the mathematical estimate. So here, the proof of the optimality of MLE is not through analyzing MLE directly, but from analyzing this estimator from an algorithmic perspective. Okay, so now we are left with the analysis of SDP. Okay, so just like the analysis of the MLE, I'm also going to analyze the solution of SDP from an iterative perspective. I'm going to write down an iterative algorithm and then relating the solution of the SDP as the fixed point of this iterative algorithm. So this actually is given by a non-convex perspective of the semi-different program. So first, let's try to briefly review what we have for the MLE. So this is the optimization problem that we have for the maximum likelihood estimator. And as we saw from the previous slide, the generalized power method characterized the MLE because the MLE can be regarded as the fixed point of GPN. Okay, and for SDP, it has a similar relation by observing that the matrix Z is always positive semi-definite. And for any positive semi-definite matrix, you can factorize Z as the product of V transpose V, right? Once you plug this factorization back into SDP, you will get an equivalent formulation of SDP. But this formulation of SDP is optimization over V, not over Z, right? So it is equivalent, but it is actually non-convex optimization, right? So if you're optimizing over Z, it's convex, but if you optimize over V, it's non-convex, right? Turns out these two perspectives, they are equivalent. And this is actually very well known as the Bierman-Terra factorization in literature, and people have been using this factorization to derive efficient algorithms to solve SDP for a long time. And it is with this non-convex representation, we can write the solution of SDP as a fixed point of this iterative algorithm, right? So for this iterative procedure, it is very similar to the formula that you have in the power method. You can actually view this as the generalized power method be lifted from one dimension to a higher n-dimensional space. And this is what it means, okay? And next, I'm going to give a characterization of the evolution of this iterative algorithm and use that to solve the statistical property of the SDP, okay? So first, we will use this notation again, F, to denote the map that gives the evolution of the algorithm. And then we have the same lemma, which also holds for the for this evolution of the algorithm that corresponds to SDP, right? So here, the only difference is in order to measure the closeness between a matrix V and the vector Z star, we actually need to slightly generalize the loss function. But here is the definition. It's actually not very hard to write on the definition. Otherwise, it's exactly the same result as what we have already seen for generalized power method. Okay, and with this lemma, we immediately write down the statistical optimality of SDP by realizing that the solution of SDP can be factorized as V hat transpose V hat, where V hat satisfies the fixed point property. SDP achieves statistical optimality in these loss functions. And here, for the third loss function, Z hat is actually the normalized leading eigenvector of the matrix Z hat, because the output of the SDP is always a matrix. If you want a vector estimator, a post-processing step is necessary, unless you can show SDP is rank 1, but sometimes it's not. Okay, this is the upper bound that I want to, all the upper bound results that I want to discuss. So next, let me briefly discuss the lower bound proof. The lower bound proof is actually quite standard, and there's really not much to talk about. It's just a standard argument. So the first step is to write down the definition of the minimax risk. Here, the only issue that we have for the loss function is because of the extra minimization over a global rotation, which results in the non-separability of the loss function, right? So without this minimization, we have a separable loss, then you can distribute the problem to each coordinate, but now we cannot. But there is an easy trick to resolve this issue, is to use this inequality to lower bound the original loss by the Frobenius loss, okay? Which turns the problem of estimating each angle to the problem of estimating all the pairwise difference of different angles, right? And the Frobenius loss is clearly separable, and then you can use the standard argument, which lower bounds the minimax risk by the base risk. And because of the separability of the Frobenius loss, you can then distribute the ID prior to each pair JK, okay? And for each pair, we can apply the well-known Van Treese inequality to work out the optimal Bayes risk. Add everything up. This is the result of the lower bound. Okay, and that's how you can prove lower bound for not for just for phase synchronization, but for general synchronization problems. Okay, so if I have some additional time, let me also quickly go through the problem of Z2 synchronization, which is very related to phase synchronization. It's actually a simple setting. You also have the observations ZJK equals ZJZ, YJK equals ZJZK plus Gaussian noise. But here, the parameter space is even simpler. Each ZJ can only take two values, either -1 or 1. So you can regard this problem as a discretized version of the phase synchronization problem, right? Each angle is only allowed to take two values. And we also allow the possibility of missing data. And the goal is to estimate these n discrete numbers. And again, in the literature, we have three algorithms, the MLE, generalized power method, SDP, the formulas are almost identical. And here is our result. Under the same assumptions, we have first of all have a lower bound, and then we also have an upper bound for all the three methods. The only difference that you see from this result compared with the result of phase synchronization is here, the minimax risk is actually an exponential function of the signal to noise ratio, right? The reason is here, we want to estimate a discrete parameter. So in terms of the mathematical essence, this is more like a hypothesis testing problem, right? So it is known that the optimal hypothesis testing error is exponential in terms of polynomial, which gives the exponential rate that we have here. Whereas for phase synchronization, you estimate a continuous parameter, and that's why you have a polynomial parametric rate. So I want to advocate this paper by Ying-Jie Fei and Yudong Chen back in 2020. They actually they were able to prove the optimality of SDP when p equals 1. They obtained exactly this result. So our result can be regarded as a generalization of this for a general p. The reason I think their paper is so important is because the semi-different programming is known as a continuous optimization problem, right? So for Z2, for a discrete problem such as Z2 synchronization, it is not obvious it will capture the discreteness of the problem. So for a long time, what people can only establish for the performance of SDP is a polynomial rate. The paper by Fei and Chen is the first time in the literature that rigorously prove the performance of SDP for this discrete problem is actually exponential, right? That's a big achievement. And if I remember correctly, the error exponent in Fei and Chen is also sharp. They get the sharp exponent, okay? So here, our result is more general. We have a general P, but actually the major difference is the difference of proof. The proof of ours is completely different from the proof by Fei and Chen. They directly analyze ANP from the definition of the objective function, but we analyze the performance of SDP from the Baron-Montero factorization point of view. Okay? And I think this is a very good point of view because it actually allows us to compare the difference between phase synchronization and Z2 synchronization, because the way we prove the optimality of these results are actually derived from the same method, right? Both are based on Baron-Montero factorization. And here I list the different optimal error for the two SDP and also the definition of the two SDP. Well, you may be curious to notice that the definition is exactly the same. So what's going on? Actually, they are not exactly the same. I deliberately try to hide something very important, right? So the main difference between the two SDP is for phase synchronization, the optimization is over all complex matrices, but for Z2 synchronization, the optimization is over all real matrices. And this is the only difference, right? So if you optimize this objective over all real matrices, then it turns out to capture the discrete structure, which will give you the exponential rate, okay? And the reason that the fact that we have a single proof for the two different results allows us to carefully study the proof argument and to single out the following main mathematical ingredient that highlights the difference between the two results. It turns out the main difference lies in this interesting but simple to prove inequality So here, the result says the follows. We have two vectors, two complex vector, x and y. Let's assume y is a unit vector. Then, if you want to bound the difference between the normalized version of x and y, you will get what appears on the right-hand side. Okay. Now, on the right-hand side, you look at the numerator. You notice this term, which only depends on the imaginary part of y transpose x, right? And this turns out to be the term that is only present if you have complex x and y. If you replace the setting by real x and y, then this term disappears. And when you analyze the evolution of the iteration for SDP for phase synchronization problem, it is exactly this imaginary term that gives you the polynomial rate. The exponential rate is always there, right? For Z2 synchronization, this term is not present. Therefore, you only have the exponential rate of convergence, and that's the difference. Okay. All right, so that's almost the end of the talk, and I would like to use the last slide to tell you a generalization from phase synchronization to a general rotation synchronization. So here, the model is a noisy observation of the pairwise difference between two rotation. Zi, Zj are members from the rotation group SO. That's just the two-dimensional rotation, which exactly is the phase synchronization problem. Well, I don't think this is a trivial extension because we know that for SOD, the group is not commutative as soon as D is at least 3, okay? So this is actually the main difficulty for the generalization. But anyway, we are able to obtain the result by deriving a new perturbation inequality, which is sharp for polar decomposition under this context. And the results shows that the minimax rate is still of order sigma over MP, but the leading constant is given by D minus 1 times D divided by 2, right? Which turns out to be the correct degrees of freedom of the SOD group. Okay, so this is all that I want to share, and thank you for the attention. I think I can take some questions.
Thank you, Chao, for the very interesting talk. We do have time for a few questions.
Hey, Chao, this is Zoe. Thanks for the super interesting talk. I just wanted to, I have one quick question, which is, you mentioned this argument for the rank 1 case and then the rank n case for the SDP. Is it true that your argument would work for the rank k Puero-Montero factorization as well, or is there something special about 1 and n? I just want to double check.
Hi, Joe. First of all, could you tell me what rank k SDP is? Like in what context?
If I were to do the Puero-Montero kind of factorization where V is n by k instead of n by n.
Oh, I see your point.
Intermediate. Yeah, does your argument directly work in that case?
Yes, so here our k is n, and when k equals 1, it's just the power method. So your question is whether it works for general k, for example, k equals root 10 or something, right?
Yes.
Okay, I do not have a specific answer. I can only give you a very naive answer. So I believe the result will work for a k that is sufficient large. For example, it is possible that as long as k is root n, then it may work because if I remember correctly, root n is turns out to be the threshold that the algorithm give you the local, the global optimum. But we did not prove it.
Thanks. I do have maybe one other question, which is, so you mentioned in your lower bound for the complex case, you use this Ventry's argument and the standard reduction. I was wondering, is the exponential lower bound for Z2 the same, or is it something different?
For the exponential rate, everything before the Van Trees inequality is the same. And then for that particular step, it's just Neyman-Pearson, and then you can analyze the testing error directly. Even simpler.
Okay, thanks.
Hey, just a couple of questions. Thanks for the nice talk. The first one just is off the little identity you said in the end about the complex case versus the real case. So if
right,
is it correct? Is the following interpretation correct? If Z star is actually real, so it's plus minus 1, but then you use the SDP in complex space, then it's automatically adaptive, like it actually gets an exponential rate? Because that second term seems to depend on, okay.
Right, it's a very good question. If you know, so if the truth, Z star, it's either plus or minus 1, but you use SDP in a complex space, it will still give you the polynomial rate. Because here, the inequality, I didn't say it only depends on the truth. It actually depends on some other quantities as well.
I see. Okay, that makes sense. The second question, sorry, just one other quick question. So you presented this sort of in this general discrete iterative method thing that you were talking about. So when you were talking about clustering, I was thinking to myself, okay, this is Lloyd, but Lloyd is actually not consistent in the means, right? Because if you initialize Lloyd at the true means, it doesn't get you the means. And then you sort of specialized in the synchronization case by saying, okay, it doesn't really matter. You don't really care about the means. But then in the general discrete case, is there like a version of EM or something that still applies in your structural linear model?
Yes, very good question. If you want to estimate the parameter, which in my structure linear model notation is B, then for example, in Gaussian mixture model, you use Lloyd's iteration. It's inconsistent. This is actually known as the Neyman-Scott phenomena. So in general, the iterative algorithm for the general setting does not work for B, right? So it will be a very interesting direction to actually analyze a general EM algorithm, as you suggested, or maybe a variational base. And these algorithms will be able to recover, the continuous parameter B in an optimal way. But we haven't done that.
Thanks.
Thank you.
Are there any more questions? Let's thank Chao again.
Thank you.